Welcome. The topic we'll be discussing in this lecture is data hazards. Okay. So in the last lecture we have discussed that the pipeline may get stalled because of three reasons, either because of data hazards or because of instructional hazard or because of structural hazards. Okay. So this lecture will specifically focus on data hazards. What is a data hazard and when data hazard will occur and how to detect data hazard. If data hazard is detected in advance, can we do something? All those things we'll be discussing, right? Fine. So, so when you are implementing pipelining, we should ensure that the output produced because of pipelined execution should be same as that of sequential execution. Okay. See, due to pipelining, what we are doing, we are overlapping the instructions. We are overlapping the instructions, right? That is, when the first instruction is in the decode stage, the second instruction is being fetched. When the first instruction is getting executed, the second instruction is getting decoded. So we are overlapping the instructions, but this overlapping can also be called as concurrent execution. So overlapping can also be called as concurrent execution. It is not parallel. We don't have two processors. We have only one processor. Okay, but within one processor we have different units. One unit for instruction fetch, one unit for instruction decode, one for execute and one to store the result. So whenever a unit is free, we are using it for the next instruction. This is called as concurrent execution. So when such concurrent executions are happening, we should ensure that the result, because of that, it should not impact the result. Okay, the result should be same as if you are executing these instructions sequentially. Okay, so that's what being checked here. We must ensure that the results obtained when instructions are executed in pipeline processor are identical to those obtained when those instructions are executed sequentially. Okay, so a hazard occurs in this type of situation when say for example, let us call this as instruction 1 and let us call this as instruction 2. Okay, so in say we will call this as the destination operand and this as the source operand. Okay, right? So when the destination operand of the instruction 1 is being used as the source operand of the instruction 2, in such cases we may face data hazards. Okay, when the destination operand of the previous instruction is used as the source operand of the next instruction, in such cases there will be data hazard. Okay, so here you can see what we are doing. A, there is a variable a is equal to 3 plus a. It means previously a contains some value, right? Say previously, let us assume a contains 3, right? Okay, initially let us assume a is 3. Then after executing this instruction, what will be a? A will become 3 plus 3, that is 6. Okay. So if these two instructions were executed sequentially, what will be the result? First the instruction 1 will be executed, then instruction 2 will be executed. So a will be updated with 6 and it will be 6 into 4, it will be 24. Right? But if these two instructions execute concurrently, if these two instructions execute concurrently, there is a chance for wrong output. Okay, because before this instruction starts, what is the value of a? 3. Okay, so it will assume a as 3 and it will perform. But say that when this instruction is getting executed during the same time, concurrently you are executing this instruction also. Now this a is not updated to 6. So this instruction also will assume a value as 3. Then it will calculate 3 into 4, that is 12, which is a wrong answer. Okay, right? So such things should not happen when we are using pipelining. Okay, say for example, so this instruction will create a hazard. So when this type of instructions are there, we should be cautious. That is, the appropriate hardware or the software unit should be cautious when when the when the destination of the operand of the previous instruction is used as the source operand of the current instruction. Okay, but in the second case there is no hazard. Okay, here you see a is equal to 5 into c, b is equal to 20 plus c. There is a variable c which is used in both the instructions, but in both of these instructions the c is coming as a source operand. Okay, that means it is not getting modified, right? So if originally c is 5, then while executing these two instructions c will be 5. It is not going to change. Only a is changing. A will become 5 into c, which is 5 into 5 is 25, and b will become 20 plus c, that is 20 plus 5 is 25. These two instructions can be executed concurrently and it will not create any hazard. Whereas when you execute these two instructions concurrently, it may create hazard, and we should be cautious about that. Okay, right? When two operands depend on each other, they must be executed sequentially in the correct order. Okay, so here these two instructions depend on each other, so they should be executed sequentially, right? Or if you are using pipelining, then it should be stalled at appropriate place. It should be stalled. That we'll be discussing. Okay, so so here we say that these two instructions are dependent on each other, right? But these two instructions are not dependent. Okay, let us see another example. Here what we are doing, multiply R2 with R3 and store the result in R4. So destination operand is R4, source operand is R2 and R3. R2 and R3 are multiplied and the result is stored in R4. And then what we are doing, add R5 comma R4 and store the result in R6. See this, so the destination operand of the first instruction is used as the source operand in the second instruction, or the destination operand of the previous instruction is used as the source operand in the next instruction. So this will create hazard. Okay, so this should be executed sequentially, or if you are using pipelining, it should be stalled at appropriate place to make sure that the result is not getting affected. Okay, so let us see this two instructions, how it will be executed with a pipeline without affecting the final result, right? These two instructions, how it should be executed in pipeline. Okay, right? So first, that multiple instruction is executing as usual. What it is doing is getting fetched at clock cycle 1, it is getting decoded at clock cycle 2. So we are calling this as instruction 1 and this is instruction 2. Okay, so multiply R2 comma R3 comma R4 is fetched at clock cycle 1, decoded at clock cycle 2, it's executed at clock cycle 3, and its result is written at clock cycle 4. See, this is important. Result is written means what? The R4 is updated at clock cycle 4. R4 is updated at clock cycle 4. Okay, fine, right? Let us see more clarity on this. Fetch means what? This instruction 1, fetch means what? It fetches this whole instruction. This whole instruction, multiply R2, R3, R4, it fetches. Decode means what? Decode means it identifies the operand. What are the operand here? R2, R3 are the source operand and R4 is the destination operand. All these operand it identifies. What is the value of this? Then it executes and it stores the result in R4. Okay. Now instruction 2 executes. What is instruction 2? It is fetched in clock cycle 2 correctly. Okay, so in clock cycle 2 it is fetched. Add R5, R4, R6. And in clock cycle 3 it is decoding. While decoding, it understood that it needs R5, R4 and R6. But currently it can fetch only R5 and R6. Okay, during decode phase data will be fetched. It can fetch only R5 and R6. It cannot fetch R4 because R4 is during clock cycle 3 it is not available. It is written only at the end of clock cycle 4. Are you getting? So by this time the processor will understand that R4 is not available, so it will stall. It will stall. Okay, it will get stalled, right? So it will get stalled and it will wait. It is waiting. It is waiting how long? Until R4 is available. When R4 will be available? At the end of clock cycle 4. Okay. So again it is performing this decode operation. Because this decode operation is invalid. First it tried to decode. So as a result of that, it was able to fetch only R5 and R6. R4 has not been, it is unable to fetch R4. So it started waiting until R4 is available. Okay, once it came to know that R4 is available, then once again it restarts the decode operation. Okay, now it got all the operands. What are the operands? R5, R4 and R6. Now it will perform the add operation, that is what is execution is add R5 and R4, and then the output will be stored in R6, right? Okay, so because, so here you can see there is a delay. There is a delay of not one clock cycle, two clock cycles. Actual delay is one clock cycle, but decode is again executed. So you're getting decode. I mean decode operation is done once again. So this decode become invalid, right? Right. So it is as if this clock cycle become wasted. Again you are decoding here. So so the I mean so the pipeline is getting stalled by two clock cycles while executing instruction 2, right? Now in the for the further instructions also, the pipeline will be stalled by two more clock cycles. Okay, instruction 3 will be fetched during clock cycle 3, but it won't be decoded because now until instruction 2 was decoded, you cannot decode instruction 3. So after, because decode unit is not available, right? Instruction 2 is holding the decode unit from this time to this time. It's not available for anybody, right? Okay, so instruction 3 can decode only at this time, then it will execute and then it will write. Okay, right, fine. So as instruction 2 is holding the decode unit, instruction 3 is holding the fetch unit. It is not releasing the fetch unit. Instruction 3 will release fetch unit only at this time, where instruction 4 can use the fetch. So further everywhere uh, the clock cycle is, I mean the all the I mean it is getting stalled. Okay, for all instructions the pipeline is getting stalled by two clock cycles. Okay, right, fine. Now is there any way to stop this stalling process? If you somehow know that there is a, what you call, there is a dependency between two instructions, so this is called as dependency. These two instructions are dependent. Okay, so somehow if you know that there is a, so this is called as data dependency. See, instead of data hazards you can also call as data dependency. Some books also call as data dependency, because here first instruction depends on the data of the second instruction. Okay, so if you know the data dependency in advance, is there any way to predict it, and can we overcome this this pipeline stall or not? Yes, there is one method. That method is called as operand forwarding. So there is a method to uh, to overcome this drawback which is created by data hazards. The drawback is the pipeline is getting stalled, and this can be removed by using a technique called operand forwarding. So what is meant by operand forwarding? So the concept of operand forwarding, what it says in the sense, see here these two instructions are dependent, right? Multiply and add are dependent. Fetch is completed at clock cycle 1. Decode is completed at clock cycle 2. Execution is also completed at clock cycle 3, which means result is available at the end of clock cycle 3. But where it is available? Result is what in this case? In this case, multiply R2 and R3, the output should go to R4. So whatever should go to R4, that result is already available at the end of clock cycle 3. But where it is available? It is available in the intermediate buffer. Where it is available? It is available in the intermediate buffer, or this intermediate, instead of calling this as intermediate buffer, you can also call it as output of ALU. Are you getting? This is available where? It is available in the intermediate buffer, or it is available in the output of ALU. Okay. In the previous class, we have discussed one diagram. You just recall that each unit, what they will do, in the sense they will fetch, they will do the operation and they will keep it in buffer. Fetch will fetch the instruction and keep it in buffer 1. Decode will take the instruction from here, it will decode and it will keep it in buffer 2. Okay, execute unit will execute and it will keep the result in buffer 3. This buffer 3 is nothing but output of ALU, because execution is what mainly ALU will be involved. Okay, this buffer 3 is nothing but output of ALU. Okay, and right after that it will write. So operand forwarding technique, what it says in the sense, operand forwarding technique, what it says in the sense, don't wait for the operand until it is getting written by the write unit, because it is going to take one clock cycle. Okay, if you want to avoid this delay, if you want to avoid this delay, this data, once it is available in this buffer, it can be directly used by the next instruction if required. This data only you are going to write to some register, right, or some memory location. This data can be directly utilized by the next instruction if it is required. So this concept is called as operand forwarding or data forwarding. This concept is called as operand forwarding or data forwarding, and here we are going to use that technique, what is called as operand forwarding. Okay, right? So that is what being explained here. Instead of from the register file, register means after writing to the register. Okay, the second instruction can get the data directly from the output of ALU or the buffer after the previous instruction is completed. A special arrangement needs to be made to forward the output of ALU to the input of ALU. Okay, so we need some special arrangement so that the output of ALU can be directly forwarded to the input of ALU, because in the next instruction, whatever the output of the previous instruction will become the input, right? So normally the calculations will be done by ALU, arithmetic logic unit. Are you getting? So the point is, the write is going to write to the registers, right? So that's what it says. Instead of fetching the data from the register file, the second instruction can directly take the data from the output of ALU. Where is the output of ALU? Here. E1 it is storing in the buffer. This buffer is nothing but the output of ALU. Okay. Then you have to make some special arrangement such that this output will go as the input of ALU in the next stage itself. So if that happens, no, then at the end of this clock cycle, this data, why it is waiting and decoding again? Because one data is not available. Which data? R4. But R4 is nothing but it is available here. So once if you are able to pass in from this buffer directly to instruction 2, now here itself R4 is available. Now you need not decode again. You need not decode again. Rather here itself you can execute. And here itself you can write. Then what will happen? There is no delay and there is no stall. Okay, so by operand forwarding technique, the stall or the delay from the pipeline can be removed. Okay, how? In the sense it is explained through this. So this is nothing but mm, the CPU configuration, which we have already discussed in a single bus and multiple bus organization. So this is a multiple bus organization. Here there are two buses. Okay, right? So here there is a ALU. These are the inputs for the ALU, source 1, source 2. One input is coming from destination, right? So if ALU performs some operation, that result will be available in RSLT, which we are calling as buffer. Okay, so you can see here the input for the ALU is coming from source 1 and source 2. Okay, whatever this input. Okay, with this input it performs an operation. So if you see in the first instruction, the input will be R2, R3. Source 1 and source 2 will have R2 and R3. So one of it will have R2 and another one will have R3. Okay, so it is going to multiply, right? It is going to multiply R2, R3, and that result will be available here. Okay, whatever the multiplication result, R2 into R3, that is what is going to get written in R4. But before that, that result is available in this intermediate register. So this same diagram it is shown in other way here. This is ALU and its input are SRC1 and SRC2. So this output is available here. After that it will be written. Okay. But now the next instruction wants this. Next instruction wants this. So what you can do, next instruction means what? Next instruction want to perform what? Execution. Execution means what? This output should become an input of ALU. So it will just go to the input of ALU. Are you getting? And what will be the another input of ALU? So R4 now you have directly given as input. What will be the another input? R5. R5. Okay. So in one of the registers you have to keep R5. That's all. We are not going to now use two registers. So say for example this result is going here. No. Maybe this will go to SRC1 and it will become as an input. So if this is R5, this will be R4. Are you getting? This output, we let us say R2 and R3 is given here. Right? So because here one input is what, R5, and another input is R4. R4 is nothing but R2 into R3, whatever that output. So that output directly you can pass through any one of the SRCs, SRC1 or 2. Here I am assuming SRC2. Then the another input will be R5. Okay. If you do that, then there is no stall in the pipeline and there is no delay in the pipeline. So this concept is called as what you call as operand forwarding or data forwarding technique. Okay, by which the stall can be eliminated in this kind of instruction where the destination operand of the previous instruction is used as the source operand in the next instruction. Okay, right. So actually here we are handling data hazards by using I'm not talking about operand forwarding, the without using operand forwarding when there is a stall. When there is a stall, the data hazard is handled here. Handled in the sense the stall is created, right? The stall is created. If you are not creating stall, what will happen? Wrong error will be created. Wrong error will come out, right? So this is also one. This is handling data hazard is also one solution, but this is a solution with delay or with stalls. Okay, but this operand forward is a solution without stalls. Okay, so if you don't apply stalls, then it will create wrong outputs, right? Fine. Now this, what you call this creating delay, these things were done by whom? This is done by hardware. Here it is done by the hardware. The hardware is detecting. The hardware is detecting that there is a relationship between this instruction and this instruction, or there is a dependency between this instruction and this instruction. And what dependency? The source operand of the second instruction is nothing but the destination operand of the first instruction. So there is a dependency. So so the pipeline should be stalled. Okay, like that it is doing. Okay, so 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 that's what it is happening here. Okay, so here the data hazard is actually detected by the hardware. So the hardware is detecting that there is some relationship or dependency between these two instructions, and it is identifying that a stall should be introduced. Otherwise, it will create a wrong error, wrong output. Okay, but instead, this can also be handled by the software. This can also be handled by the software. Software means what? Compiler. Previously, we have discussed that if you want to achieve pipelining, we need an optimized compiler. Okay, so this can also be done by the compiler. Then the load on the hardware will be decreased. Okay, if the compiler detect that there is a data hazard or there is a dependency between two instructions, then what the compiler will do in the sense, say here the compiler has identified that this instruction and this instructions are dependent. Instruction 1 and instruction 2 were dependent. That is, the instruction two's source operand is nothing but instruction one's destination operand. Okay, so it cannot be executed concurrently. If pipeline is used, it should be stalled appropriately. How many cycles it should be stalled? 2 clock cycles it should be stalled. So it is introducing a in the as the compiler output. When this program is passed through the compiler, actually the user has written, the programmer has written after this line, he has written this line. Okay, but compiler in between that it will introduce two no operation, no operation, which means that there are two no operation means the what you call, the hardware will wait for 2 clock cycles. The hardware will wait for 2 clock cycles before executing instruction 2. Are you getting? After executing instruction 1, if hardware sees that, if the processor sees that there is a no operation, then for 1 clock cycle it won't execute anything. Then for another clock cycle also it won't execute. After that only it will execute this instruction. Okay. So here we are not loading the hardware, like hardware should detect whether there is a dependency or not. Rather it is detected by the compiler itself, and it adds appropriate no operation so that during that time this instruction will not be executed. Only this instruction will not be executed. That doesn't mean that CPU should not execute any instruction. Some other instruction it can execute. For example, there may be some other instruction from some other program. So during that, this no operation time, it can execute that instruction. Similarly, during this no operation time, if there is some other instruction which is not at all data dependent, that instruction can be executed, maybe from this program or some other program. But the point is, these two instructions should be separated by two no operations, that is two clock cycles, so that there will not be any what you call inconsistencies with the result. Okay, so if this data hazard is identified by the software, that is by the compiler, that is called as handling data hazards from the software end, right? Okay, so right. And there can be some side effects with data hazard. What are the side effects in the sense? See, in the previous example, we have discussed that data hazard is directly identified by the, I mean, the whatever the example we have discussed is a straightforward example. Like the first instruction's destination operand is the second instruction source operand, but always that may not be the case. For example, if you consider this instruction, here what we are doing, add r1 comma r3. We are adding the content of r1 and r3, then add with carry r2 comma r4. If this instruction created a carry, it may create or it may not create. Are you getting? It may create or it may not create. If it creates a carry, then that carry should be included, right? Then that carry should be included. Okay. So, so this kind of instruction may, for this kind of instructions, it is not that easy to identify the what you call the data hazard, the data hazard. Okay. So, uh, so so the hardware, the hardware should be very what you call it should not be checking only for destination operand and source operand kind of thing. This kind of, for example, why we cannot see this instruction, it should be executed in this order only, because only after executing this you know whether there is a carry or not. Are you getting? Until this instruction is not executed, you don't know whether there is a carry or not. If there is a carry, then you have to add what, r2 r4 plus carry. Carry also should be included. If there is no carry, then you need not add carry. So for this second instruction, what are the operands? If there is no carry, then there are only two operands. If there is a carry, then there is three operands. So for the second instruction, whether there is two operand or three operand, that is actually depend on the first instruction. Are you getting? But in the first instruction, there is no destination operand. I mean, the destination operand is R3. That is not used as the source operand here in the first instruction. But still, these two instructions are dependent instructions. Okay. So the hardware, if the hardware is detecting the hazards, then the hardware should be able to detect this type of dependencies also. If software is detecting the hazard, then the software should be able to detect this type of hazards also. So these are called as side effects. Okay. So not all data dependencies will be straightforward. Some of the dependencies may not be straightforward at all. By just seeing the instruction, we may not be understand we may not be able to guess whether there is a dependency or there or not. But still, there may be dependency. Okay, right? Fine. That's it about this topic. So we'll stop here. Thank you.